Good evening, friends. So today we are going to discuss about the main differences between a microgrid and a virtual power plant concept. So let's see through a case study how a microgrid is different from a virtual power plant. You can see here the first one is the microgrid business case and the second one is a virtual power plant business case. So in the first case, there is direct transaction between microgrid operator and the end consumer. Also between the micro source and the microgrid operator. But in a virtual power plant, we don't have a direct transaction between the end consumer and the virtual power plant operator. There are intermediaries in between. That is, an energy market is there and an energy retailer is there. Direct transaction is between the end consumer and the energy retailer. So basically whatever is the market price here, at that price the retailer is buying power and it is distributed among the end consumers at a different price so that the energy retailer gets a profit. Okay, so because of the removal of the intermediary in the microgrid case, the stakeholders have better profits or rather better benefits that we'll see from the example. Now the end consumer has a demand of 0.165 a demand of 100 kilowatt hours and he buys power from the microgrid operator at 0.165 euro per kilowatt hour. So he is paying 16.5 euros to the microgrid operator. But this power, that is this energy, that is 100 kilowatt hours energy, is bought from the energy market at 0.15 euros per kilowatt hour. Okay, so 30 kilowatt hour is bought from the energy market and 70 is bought from the micro source. So 70 plus 30 is total 100. Okay, so this 70 is bought at 0.1 euro per kilowatt hour and this 30 is bought at 0.15 euro per kilowatt hour. So 4.5 euros is paid by the microgrid operator to the energy market, and the microgrid operator pays 7 euros to the micro source. So the total expense is 7 plus 4.5, which is 11.5 for the microgrid operator, but he gets 16.5. So 5 euros is the profit for the microgrid operator. Now the microsource gets 7 euros, right? His cost of generation, this is not cost of generation, basically he gives energy at this price, 0.1 euros per kilowatt hour. Now let's see what is the difference here in this case. Here the microsource is not directly, there is more than one intermediaries in between the microsource and the end consumer. Here only one intermediary is there, which is the microgrid operator. The microsources are giving energy to the end consumer through the microgrid operator. Here the microsource is giving energy to the end consumer through the VPP operator and the energy market and the energy retailer. Okay, so here at the same price the microsource is selling his energy. So the 70 kilowatt hours is bought by the VPP operator here. The same 70 kilowatt hours was bought by the microgrid operator in the microgrid business case. Here it is bought at the same price. So 7 euros is paid by the VPP operator to the microsource. Now this same 70 kilowatt hours, he cannot directly sell it to the end consumer, or he cannot directly distribute it. So through the energy market he should go. So he sells it to the energy market at the market price. The market price is 0.15 euros per kilowatt hour. So 0.15 at this price 70 kilowatt hour is bought and he gets 10.5 euros. Okay, he gets 10.5 euros. Now he sells it to the energy retailer. This 100 kilowatt hours is sold at this price, 0.15 euros per kilowatt hour. So 70 is received from the VPP operator, and of course this is a pool, so more energy I mean, it has more potential. So extra 30 can be taken from the market, and he is giving because other generations are also there. So 100 kilowatt hours is bought by the energy retailer. Now this 100 kilowatt hours is sold to the end consumer at 0.2 euros per kilowatt hour. Now he gets 20 here. The energy retailer gets 20. Now what is the expense of VPP operator? It's 7 euros, right? What's the revenue? 10.5. So 3.5 is his profit. This VPP operator's profit is 3.5. Now what about energy market? His expense is 10.5. His revenue is 15 euros. So 4.5 is his profit, right? Now what about the energy retailer? His expense is 15 euros and his revenue is 20. So 5 euros is the profit for the energy retailer. So the 5 euro profit here, I mean, the profit of microgrid operator was 5 euros in the microgrid business case. For the same profit for the energy retailer, the end consumer had to buy energy at a higher price. It was 0.165 euros here, it's 0.2 here. Okay, so and for the VPP operator, it's actually shared by the energy retailer, energy market, and the VPP operator here. Okay, here only two intermediaries are there. Actually, energy market is not an intermediary, because if local consumption, maximum local consumption is encouraged in this case. If the end consumer gets the whole gets his demand satisfied from the microsource itself, then the microgrid operator is not he's not required to approach the energy market. Here to balance the market, he goes to the balance the demand generation, he goes to the energy market. Here definitely he has to go through the energy market. So more intermediaries. So this is the basic difference between virtual power plant and microgrid with respect to business transactions. Now we will see the structure. What is the structure of a VPP and a microgrid? So you can see here there is no direct connection between the VPP and the local load. Right, it is through the wholesale market and the retailer. Okay, central generators, of course, this is the wholesale market in the sense grid, upstream grid, the market associated with the upstream grid. So central generators are connected there, other loads are there, bulk loads are there, and power can be purchased from here to the VPP, or power can be pumped to the wholesale market also. But power that is purchased from the wholesale market is for loads, right? But load has no direct connection with the VPP. So it's through the retailer only. So the retailer is not here. The retailer is not able to get power directly from the DERs, the distributed energy resources. It's through the wholesale market. Here it's not the case. Here the retail market has direct connection with the local load, and of course and with the DERs also. Okay, so with the local load, what happens is whatever is the demand of the load demand of the local consumer is expected to be satisfied from the local DERs through the aggregator. And if there is a deficit in power, he can take it from the wholesale market just for balancing. Okay, here local generation is encouraged more. Okay. So more flexibility is there in the case of microgrid. That we'll see with another example. 1 minute. Okay. Now, this is commercial VPP, CVPP. Then this is technical VPP, TVPP, and this is microgrid. So let's see first what is commercial VPP. So the upstream grid price or the wholesale market price is 0.15 euro per kilowatt hour here. And the line capacity is 100 kVA. The maximum line carrying capacity is 100 kVA. Now the local generation is 200 kilowatts. And the cost of generation here is, this can be cost or price. Okay, 0.1 euro per kilowatt hour. Now here it is 50 kilowatt hours. So basically 200 minus 50, 150 is pumped to the grid. So the line is overloaded by 150%. Now here the concept is that the system is always looking for cheaper power. This is commercial. So commercial objective is more what to say emphasized here. Basically you know that the upstream grid price is 0.15 and the local generation cost is 0.1. So which one is cheaper? This is cheaper, right? This is cheaper. So 200 maximum generation is from here, and that is why it is pumped to the grid. But here what happens is technical constraints are also taken into consideration. So here 150% overload is not allowed. See, this 150 can vary. Okay, for a commercial VPP, keeping in mind the commercial objectives, it may be 20% overload also. This can be 120% also. This is just an example to explain what is emphasized in each case. That is a purpose of this particular example. So here it's 90% loading because this 200 is back down to 140 kilowatts. We know that we can sell more power and earn more from the local generation point of view. But still, because of the maximum power carrying capacity of the line, we only generate 140. But the load is untouched here, right? The load is untouched because here there is no transaction between the load and there is no direct transaction between the load and the operator, right? As we have seen in virtual power plant, there is no direct transaction between the operator and the load, the local load. The local load is transacting only with the retailer. So the operator may not be directly communicating with the load that there is a problem with the line carrying capacity. The constraint is already hit, so you have to adjust your load demand, or flexible demands are not that encouraged in virtual power plants because it has no direct connection with the operator. But in the case of microgrid, what happens here is now the generation is increased from 140 to 160, right? This load is also changed from 50 to 70. Suppose you have a battery here, an energy storage here. So and you are able to extract more power from the local node here. That is the local generator connected node. So in this case, again 90% loading only, but load is touched here. So the consumer has more flexibility in case of microgrid. Here that is not there. Okay, so that is what is technical and commercial virtual power plants. Now moving on to the operation strategies. Different microgrids have different objectives to be satisfied. That means the operator has different objectives. It can be more inclined to commercial objective, or it can be more inclined to technical objectives. It can be sometimes inclined to environmental objectives. So it depends. Okay, it depends on the policy. Now, the economic mode. The first one is economic mode. So you can see here DG, operation cost and revenue. If this is the objective function. So basically we are going to optimize the operational cost and revenue. That means if you want to maximize the profit, the revenue minus operational cost is the profit, right? This has to be maximized. And the profit is a function of all the active power outputs of the local generation sources, or if demand response is also there, then that will also be a control variable. So basically profit is a function of profit of P1, P2, P3, etc. Some n number of sources are there, then up to Pn it will be there, active power sources. And we can include reactive power also if there is a reactive power pricing model in the settlement process. But it depends. So basically the main objective is economic objective, that is maximization of profit. The economic mode assumes DGs are operated with full liberty and bear no grid or emission obligations. So here in this objective, technical constraints are not included and emission constraints are not also included. I mean, they are also not included. Constraints in the sense limits may be satisfied, but it's not included in the objective function. Suppose we are taking nodal voltage deviations as the objective function. That means if the actual voltage of the node is Vi actual voltage of the ith node is Vi, and the reference voltage or the nominal voltage of that particular node is Vref. Then Vref minus Vi should be minimized, right? That is the voltage deviation. So if that is included in the objective function, that is a technical consideration. Here we are not doing it. This is just economic consideration and we are going for profit maximization. Okay. Now, so here emission cost is included. So if environmental objective is there, it should be encouraged. It should be encouraged using some incentive, right? Based on carbon emission, if there is a cost for emission, then the use of renewable energy sources could be encouraged. So environmental objective is also considered. But basically all these are converted into cost because this is economic mode. Okay, outage cost, loss cost, reliability, power loss, voltage, grid voltage and loading. Here these are constraints. DG physical limits, energy balance. This is equality constraint, energy balance. Basically power generated minus power, the power demanded minus power losses, network losses equals 0. So this is an equality constraint. Now here DG physical limit for each distributed generator, there will be P min and P max, active power minimum and active power maximum. Then here grid voltage and loading, as I said, voltage deviations can be included. Power loss, but power loss is not considered in the objective function, right? That is why I told this is just an economic mode. If power loss is an objective function, then minimization of power loss itself would be the optimization problem. And power loss is of course a function of different active power outputs of the distributed generators in the system. Now GHG emission, this is environmental objective. So here this is economic mode. Main limitation comes from the physical constraints of DG, because each DG has a Pmax. Beyond that we cannot go. So right, we cannot generate beyond that. So that is a constraint. Based on that, the economic objective is constrained. It is limited. We cannot maximize the profit in the most flexible manner, right? As there are constraints, it may not go that much high. It will be limited. It will be capped. The profit will be capped. Now, going to the technical mode. See, the objective function has now changed. It has changed from here to here. Loss cost. So if power loss is converted into cost, and if that cost is minimized, minimizing this particular cost, again, the control variables are active power outputs. It can be reactive power outputs also. Okay, it depends. So this is basically changed. The technical mode assumes distribution system operator has complete control over DG operation and does not care for economics. Okay, so here loss is the first thing that is considered, not the operational cost and revenue. Even though the profit goes to a suboptimal point, we emphasize on the loss cost. And constraints are grid voltage and loading, DG physical limits, energy balance. So now constraints are increased. These two constraints were there, DG physical limits and energy balance. Here grid voltage and loading is there, but it's not a constraint. Here it's a constraint. So you can even impose strict constraints, more stringent constraints. Suppose 5% margin is allowed for voltage, then it can be from 0.95 to 1.05, right? But if you are more emphasizing on, if you are emphasizing more on technical constraints, then you can make it 0.98 to 1.02. So that is what. So basically the stress is different. Here stress is given to economy, here stress is given to technical things. Then now comes the economic mode. So slowly it shifts from the loss cost to the emission cost. Now we are emphasizing on minimizing the emission cost. The environmental mode assumes DG dispatch is solely determined by emission quota. Okay, only DG physical limitations, power on off durations are considered. For constraints, DG physical limits and energy balance is considered, but grid voltage is again taken out from the constraint. So, but the basic limit is will not be violated. Okay, otherwise we cannot operate the system. So that will be there, of course, as technical constraint, but it's not that stringent. That's what is the meaning. So that's all with the DG and microgrid part. Now we'll slowly move on to peer-to-peer transactive energy markets, which is comparatively a new area compared to the already existing wholesale markets. That we'll start that topic from the next lecture onwards. Thank you.